The way we teach trig at this college is not unique, but it does seem to be a little bit different than the right triangle approach that many colleges take. We're going to start with the unit circle. And why is it called the unit circle? Well, let's understand a little bit about this circle. What's the center of this circle? 0, 0. What's its radius? 1. So it has a radius of 1. Ergo, we call it the unit circle. Now, let's draw a few things on this circle. I'm going to label that angle theta. And angle theta has a radial line that comes out to the edge of the circle, landing at a point called P, which has coordinates of x and y. So let's make a few definitions here. We're going to start with our x-coordinate. The x-coordinate is going to be the cosine of theta, or the other way around. The cosine of theta is the x-coordinate of your point on the unit circle. Y equals the sine of theta, and the ratio of these two, when I look at y over x, is really sine over cosine, and sine over cosine is tangent. Tangent of theta. Okay? Let's keep going with the reciprocal functions. If I take the reciprocal of this, x over y, or cosine over sine, what function is that? Cotangent. I could take the reciprocal of the sine function, 1 over y, is the cosecant of theta. What's the reciprocal of the cosine? Good, secant of theta. So those are your trigonometric functions, your 6 basic trigonometric functions. Let's use these two functions to start proving some identities in trig. Now, I'm not going to be asking that you know a ton of identities in trig, but the first one I'm going to come up with is something that you should have just down pat, always. If I replace x and y by sine and cosine respectively, I'll get something like this. Cosine of theta squared plus sine of theta squared equals 1. Typically, we don't write it like this. How do we write it? Well, we kind of get rid of the parentheses and write cosine squared of theta plus sine squared of theta. This means this. It means you're taking the whole function value and squaring it. You're not squaring just the angle. So this is the Pythagorean theorem. Definitely you should have this one memorized, because from here we can get other things. So let's do that. Let's figure out some other identities. An easy way to get an identity, another identity, is to move one of these to the right-hand side, like the cosine squared to the right-hand side. Now you've got an expression for sine squared. If you want to take the square root on both sides, plus and minus square root, now you've got sine all by itself. But more often than not, what we're more interested in is something like this. We're going to take the Pythagorean theorem and divide everything through by, say, cosine squared of theta. And let's see what comes out of this. Well, the first thing that comes out of this when you simplify it is a 1. What do you suppose sine squared over cosine squared is going to equal? Tangent squared. And then finally, 1 over cosine of theta squared, secant squared of theta. But with one quick step, dividing everything through by cosine squared, we get a whole another identity. So if you know this one, you can get this one pretty much for free. I've been teaching this course since 19 mumble, and I still don't have all these things memorized. I won't ever. It's just not worth my time and mental energy. Whenever I want some more of these identities, I'll just divide and think of them that way. And what I want you to try is this. Take this identity and divide through not by cosine but by sine. See what other identity you can come up with. Sure. Okay. So, who else? Amelia, thanks for volunteering. If I divide through everything by sine squared, what will I get? Perfect. 1 plus cotangent squared equals cosecant squared. And again, it's the same kind of thing. Cosine squared divided by cosine squared is 1. Sine squared, or excuse me, actually, I guess the order's switched a little bit, but that's all right. From right here, you get cotangent squared plus 1 equals cosecant squared, but the order doesn't matter. So thanks. So there you go, 3 quick identities, and you can get a couple more by moving the 1 to the other side by dividing this through by various things. Let's move on down to this part over here. This is for right triangles only. I ran across something interesting that recently that really amazed me, and that is humpback whales that spend their summers gorging themselves off the waters in Juneau, Alaska, after putting on about 30,000 pounds of weight during the summer, travel 3,000 miles in a straight line to Hawaii. But that's just amazing. Hawaii is just a small little dot of islands in a huge ocean, and yet they find their way without missing it. So that's pretty impressive. They don't have much margin for error, I don't think. In any case, that kind of trigonometry problem is going to involve some right triangles. And when we're dealing with right triangles, we can deal with an adjacent side, an opposite side, and what's this last one called? Hypotenuse. Now, hypotenuse is kind of a strange word. It's really a Greek word that reflects some Egyptian origins. The Egyptians, when they used to build their pyramids and stuff like that, had a special kind of engineer. It's called a harpodonapta. Basically, he was a rope stretcher, because they would stretch ropes, three knots on one side, 4 on the other side, and 5 on the other side. So you might recognize 3, 4, 5 as being a Pythagorean triple. 3 squared plus 4 squared equals 5 squared. That meant that you had a right angle. And that's what you need to work with right triangle trigonometry. Now, when they had that right triangle, when everything lined up good, they're like, hey, perfect. Now, the Greek interpretation of that, hypotenuse means stretched against, because these engineers would lay down these ropes to make sure that they had right angles. So hypotenuse, there's a little history there for you. Now, the other part of this is probably a familiar, or hopefully familiar, acronym. SOHCAHTOA. What's that all about? All right, good. Sine is the opposite side over the adjacent, or over the hypotenuse, I should say. Cosine, adjacent over hypotenuse. And tangent, opposite over adjacent. So when we're working with ratios of sides, you can kind of rely on SOHCAHTOA a little bit. This is going to help you come up with some of the exact answers that we're going to need in this class. but sometimes you need to work with specific angles. Calculus is done in radians, and more often than not, they're going to expect exact answers, even when you're working in radians. So let's fill in the points on the unit circle for some special angles. And before we get going on that, let me help you out, show you a little way that you can help yourself remember these special points. Let me start by writing down a small pattern. Square root of 4 over 2, square root of 3 over 2. Can anyone tell me? Go out on a limb. What's the next one going to be? Square root of 2 over 2. Can we keep going? 1 over 2 and 0 over 2. Now, of these 5 points, 3 of them will simplify. The first one's a 1. Second one's doesn't simplify. Neither does the third one. But the fourth one does, and so does the fifth one. So those 5 points, those 5 numbers, are going to help us fill in the coordinates on this entire unit circle. Let's start out on the origin at 1 and 0. Well, it's just actually just a 1. Yeah, it's going to be a 1 and 0. But then we'll kind of move up here. The next point is going to have coordinates of square root of 3 over 2. And the point after that, square root of 2 over 2, 1/2, and finally 0. So those are all your x coordinates. And they follow exactly the pattern that we just set down. What are we going to do for the y coordinates? Yeah, just the same pattern going down. So a 1, square root of 3 over 2, square root of 2 over 2, 1/2, and 0. So going up and going down. Well, that's great. That's just for the first quadrant, though. What if I wanted to stretch things over here, like at 120 degrees in the second quadrant? Good. Which sign is going to change on which coordinate, the x or y coordinate? X coordinate. So you're going to have another one here at negative 1/2 and square root of 3 over 2. And so on. And you can do a few more. If I wanted to drop down here into the third quadrant, then I can reflect one from the first quadrant over to here. Both of these are going to have negative signs. So it's going to be negative square root of 3 over 2 and negative 1/2 at 210 degrees or 7 pi over 6. How about one last one over here at 360 degrees? Scott, what are the coordinates going to be there, please? Perfect. Thank you. So in doing this, and I'm not going to fill in the rest of this, but in doing that, you can work your way all the way around the unit circle and come up with all the points you need, all the exact values. In class on your exams and in the book for a lot of answers, they're going to be expecting exact values. And we'll talk about a different way to come up with some of these exact values. But for now, you've got them, or at least you can get them. One last thing about these, if you start thinking about sine as being, your y coordinate and cosine as being your x coordinate and tangent as being the ratio of those two, then you're going to realize that all of your trig functions are going to be positive in the first quadrant. But when you move over into the second quadrant, only the y coordinate is positive. So anything that involves an x coordinate is going to be negative. So that means the only thing positive in the second quadrant are going to be your sine functions and the reciprocals. Down in the third quadrant, interestingly enough, if it involves x and y, negative divided by negative is positive. So tangent and its reciprocal are going to be positive. And finally, cosine is positive in the third quadrant. Cosine and its reciprocal. So the mnemonic device for this is all students take, on the blank, calculus. Yay. All right, yeah. All students take calculus. So all your functions are positive here. Sine and its reciprocal are positive here. Tangent is reciprocal. So tangent and cotangent, and cosine and secant are positive there. So just something to keep in mind about your trig functions. Now let's actually find some exact trig values. Yes?
So, just to be clear, what are these? I know that the letters, I guess, what do they represent?
This is it's a mnemonic. It helps you remember what trig functions are positive and in what quadrants. Trig functions. So these 6 right here. So all of them are positive in the first quadrant. Sine and its reciprocal, so these 2 are positive in the second quadrant. Tangent and its reciprocal are positive in the third quadrant. And cosine and its reciprocal are positive in the fourth quadrant. So all students take calculus. So let's calculate a few exact trig values. We'll start with sine of 2 pi over 3. And I'm going to throw in a bunch of examples here. Let's also do tangent of 5 pi over 4. Cosine of 3 pi over 4. Cosine of 7 pi over 6. Sine of 11 pi over 6. Cosecant of 11 pi over 6. And one last one, a little bit more challenging, secant of 7 pi over 6. For starters, sine of 2 pi over 3 is just going to be the y-coordinate of your point on the unit circle. Now, I don't think we worked all the way down. Yeah, actually, we did. What's the y-coordinate at that point? 2 pi over 3. So the y-coordinate would be square root of 3 over 2. So that's going to be your sine here. Square root of 3 over 2. That's an exact value. If I ask for an exact value, please give me that. Something involving square roots. Don't give me 0.866 something. All right? That's just a decimal value. I want the exact value. For the tangent here, tangent of 5 pi over 4, you could think of it separately as a sine of 5 pi over 4 over the cosine of 5 pi over 4. First things first. Whoa, yeah, question?
If you're using pi over 4 as a reference angle, wouldn't it always be 1 or -1?
Yes. Tangent, yeah, at that point, yes. What quadrant is 5 pi over 4 in? Anyone? Third quadrant. So do you expect sine to be, or tangent to be positive or negative there? Positive. So earlier today made a little mistake, but we'll fix it now here. Sine here is going to be negative square root of 2 over 2. Cosine there is also negative root 2 over 2. When you divide these two, what do you get for a quotient? 1. Good. So our answer is 1. And it makes sense that it's a positive answer. We expected a positive answer. Okay. Why don't you try a couple more? I'll walk around and help out. When it gets to the last one, I'll help you rationalize this. If you can rationalize it yourself, that's great. But try a few of these. See if you can come up with some exact trigonometric values. Some exact numbers like we have here. sorry I don't have time to run everyone today. It's a little bit rushed. I do suggest you spend a little time with this stuff. Unfortunately, you are going to be asked for exact values quite often. Let's take a look at a couple of these. The x-coordinate at 3 pi over 4 is going to be negative root 2 over 2. At multiples of pi over 4, it's always going to be plus or minus root 2 over 2. How about the cosine of 7 pi over 6? What's the x-coordinate there? Good. Negative root 3 over 2. Sine, this one should work out pretty nice. Negative 1/2. Now for the cosecant, that's going to be 1 over the sine of 11 pi over 6, or 1 over negative 1/2. I would appreciate you simplifying that. What do you get? Negative 2. Last but not least, secant of 7 pi over 6 is going to be 1 over cosine of 7 pi over 6. And I don't know if you noticed, but these dovetail nicely. That's going to be 1 over negative square root of 3 over 2. At the very least, I expect this. Now, I sometimes feel a little bit sheepish about demanding that you rationalize it. You will find it rationalized in the book. I'm not going to worry about it too much. If I really want it rationalized, I'll tell you. But in order that you check yourself in the book, then let me remind you how to do that. You're going to multiply by root 3 over root 3, effectively multiplying by 1. But in the denominator, the square root of 9 is 3. So that's what you would see in a book. Now, there is a little bit of a cheat you can do on some of these. If you're looking at these and going, oh, I just don't remember these things. That's fine. Hey, I understand it. With your calculator in Radian mode, and the cool thing about the new ones is they are in Radian mode, you can do sine of, say, 3 or 2 pi over 3, 2 pi divided by 3. Now, it's going to give you a decimal value. But if you keep in mind two decimal values, that is, square root of 3 over 2 is approximately 0.866, and square root of 2 over 2 is approximately 0.707, then, you can really do yourself a little bit of a favor. So when I do this, I get 0.866. Oh, okay, that's square root of 3 over 2. Great. Or maybe if I did something different, I could get negative square root of 3 over 2. So it just kind of depends on where you're at. But it is a way to help you figure out what exact trig value you're working with. All right. I got to kind of rush things up. I don't know why this is taking so much longer than I did my morning class. I do have a video from my morning class, and I think I'm going to end up having to use that one for today because we made it a little bit farther. But let me finish up with some inverse trig functions. Inverse trig functions. So just like our other functions, trig functions have inverses. And by inverses, I am not counting the reciprocals. The inverse of the sine is not the cosecant. So if I wanted to solve for theta, I get theta equals the sine negative 1 of y. And really what this is, it's the angle, angle, whose sine is y. So if I take the sine of that angle, I should get y. And that angle is going to be in the range of negative pi over 2 to pi over 2. So let's do an example. Let's do an easy one. Sine negative 1 of 1/2. So what is this? This is the angle whose sine is 1/2. Basically, the angle who has a y coordinate of 1/2. Somebody already mentioned it. What is that? All right, 30 degrees. In calculus, we work with radians, so what's 30 degrees in radians? Pi over 6. All right. Cosine of, say, square root of 3 over 2 would be the angle in 0 to pi whose cosine is square root of 3 over 2. So what angle has this as its cosine in the first quadrant? Same thing, pi over 6, 30 degrees, pi over 6. So this has nothing to do with the reciprocals at all. Please don't try and find this, the secant of something by pressing the cosine inverse button. You can get these numbers off your calculator. You might want to put your calculator in degree mode, because if you were to take the cosine or sine inverse of 1/2, I mean, I don't think many people are going to recognize the decimal value of pi over 6. Let's take a look here. So second sine 0.5. There's a decimal value of pi over 6. I got to be honest with you. I'd be hard pressed to look at that and go, oh yeah, pi over 6. But if you put it in degree mode and did the same problem, you get 30. That's an angle you recognize. And then you can change it over to degrees as needed. So that's what we'll finish up with, is converting. If we go once around the circle, how many degrees is that? 360 degrees. How many radians is that? 2 pi. So if I divide this out, I get 180 degrees equals pi. And it's this equation that gives me a ratio that I can use to change from degrees to radians or radians to degrees as needed. So suppose I want to convert 330 degrees to radians. The trick is to multiply 330 by 1. The form of 1 that you're going to choose is going to cancel out the units of degrees. Exactly, pi over 180. And the first thing I'll do is I'll cancel out the degrees. And the second thing I'll do is I'll make my calculator do some work for me. So I don't want to use my brain right now. I've been thinking all day. So I'll take and type in 180 into 330. Then hit the math key and press answer to fraction. So it's 11 pi over 6. Wow, nice. So this turns into 11 pi over 6. Just don't put in the pi when you do the answer to fraction stuff. If you had to go the other way, convert, say, 315 degrees. No. Convert 5 pi over 4 to degrees. It's kind of the same process. We've got 5 pi over 4. Again, you want to multiply by 1. But how am I going to change things this time? 180 over pi. And that allows the units of pi to cancel out. And you'll be left with units of degrees. 4 goes into 180 45 times. 45 times 5 is 225 degrees. We'll stop it here. As soon as I can, I will post a video online for this stuff. I do want to give you some homework. This is the kind of stuff that I expect you to be able to do. I mean, technically, all this stuff is prerequisite. And you can also find this on the website. If you go to the course document section, look at the course notes there. You'll find this in there, but you should be able to calculate some inverse values, give me some exact solutions, And there's some trigonometric equations as well. So, whoops. You can get that, you can take a picture of it right now if you want, or you can get it off the website. So, let me just kill this here.